Good morning, everyone. We're going to get started in about 1 minute. We'll be right back on. Good morning, everyone. This is Anthony Eggert with the UC Davis Policy Institute. I want to welcome you to our webinar today. The Policy Institute is a new institute here at UC Davis, relatively new institute at UC Davis that's set up to leverage university expertise to inform better policy and practice. We're very pleased today to be partnering with the National Center for Sustainable Transportation, which is a consortium of 6 leading universities committing to advancing an environmentally sustainable transportation system through cutting-edge research, direct policy engagement, and education of future leaders in policy and practice. The center is focused on achieving that through 3 different guiding themes, including low-carbon infrastructure and efficient systems operation, zero-emission vehicles and fuel technologies, and low-impact travel and sustainable land use. One of our key partners is Georgia Tech, one of the 6 universities, and we're going to be hearing from Ann Hsu, who's going to be presenting today on the fuel emissions calculator for transit, bus, and rail technologies, and I'll introduce her here in a second. Again, want to just welcome everybody to this webinar, let you know that this is being recorded. The way that this is going to work is we're going to have about half of the time of the 1-hour webinar is going to be dedicated to the presentation from Ann. Then we're going to be hearing from a practitioner in the transit area by the name of Tommy Edwards, and I'll also introduce him at that time. But we also want to make sure that we have ample time for your questions. And the way we're going to do questions, given the number of folks we have participating, is we're going to be doing it through the webinar software. So if you have your ReadyTalk window open, on the lower left-hand corner, you're going to see a chat box. You can type a question into that chat box to the presenter, and then we'll be doing a facilitated Q&A with both Ann and Tommy at the conclusion of the presentation and the opening remarks. All of the slides can be found on our website at policyinstitute.ucdavis.edu under webinars. You should be receiving a link to that regard as well. So let's go ahead and get started, and hopefully Ann is on remotely and unmuted. Ann is a research engineer at the School of Civil and Environmental Engineering at Georgia Tech. She is the primary developer of the Federal Transit Administration's Fuel and Emissions Calculator that is done in collaboration with Oak Ridge National Laboratory. Dr. Hsu will be part of the team that's going to be expanding this tool to include heavy-duty vehicles as part of the National Center activities, and she'll probably say a little bit more about that. So, Ann, if you're on, go ahead and take it away.
All right, thanks, Anthony. Good morning, everyone, and good afternoon for the folks on the East Coast. Thanks, and welcome to the first webinar of the National Center for Sustainable Transportation webinar series. I'm honored to be the first presenter. So today, the presentation is going to be about the calculator. First, I would like to acknowledge my team members, D.Y. Lee, Franklin Golobar, Drs. Michael Rogers and Randy Gensler. We received funding from the Federal Transit Administration for the development of the FEC, and now we're receiving additional funding from the NCSC for model updates and additional analysis. We would also like to thank our colleagues at the Oak Ridge National Lab, especially Diane Davidson, Zhenhong Lin, James Lee, and Tim LeClaire. I think James is actually on the call today, which is great. So I'm going to talk a little bit about the background of the calculator, our objectives, how it came along, and then the architecture, the modules of the calculator. Then I'm going to spend quite some time talking about examples, how you can use this calculator in practice. So our overall objective was to develop an easy-to-use tool to compare multiple technology and fuel combinations within the context of local conditions and transit operations. And some of the key operational characteristics we wanted to include speed, number of stops, and grade, and passenger loading. So we wanted to go beyond national average fuel economy and instead give each transit agency the option to evaluate different alternatives within their own context of operations. And we wanted the model to have enough technical sophistication, but at the same time, it's very easy to use. To achieve this, we chose the activity-based bottom-up approach as our modeling approach. So a little more background on this. There are two primary approaches when it comes to estimation of fuel consumption and emissions. The first one is the fuel-based top-down approach. So this approach is based on fuel use or average fuel economy. So, the famous GREET model, the Fleet Footprint Calculator, uses this approach. Also, the Travel Matters emission calculator by the Center for Neighborhood Technology uses this approach too. And the other approach is the activity-based bottom-up approach, which EPA's MOVES model uses. And these two approaches are both valid approaches, and they should match up very well when the analysis are done right. We chose the bottom-up approach because it's capable of analyzing the effects of different operating scenarios in a specific area. So in the transit context, for example, it is often not possible to obtain fuel receipts for a bus on a specific route, because normally a bus would serve several routes, at least two routes on a particular day. So if a transit agency would like to compare different routes and would like to assign say they only have a small portion of the fleet that is an alternative fleet, say hybrid bus, and they would like to assign these buses to the routes that the buses are most efficient on, the fuel approach is going to be difficult because you don't have the fuel receipts on these particular routes. Instead, if you have the vehicle activity, so to speak, speed and acceleration profiles on that route, you can use the bottom-up approach and compare different routes. Also, this approach gives better estimates of air pollutants and other greenhouse gases than CO2. So these emissions are often related to fuel controls instead of fuel consumption. Using this approach, we evaluate both bus technologies and rail technologies. There is a plethora of technologies we include in the calculator, including the conventional engines, the battery electric buses, hybrid electric buses, plug-in hybrids, and hydrogen fuel cell. So, and in terms of fuels, we include gasoline, diesel, CNG, different biodiesel blends, and of course electricity for battery electric and hydrogen for fuel cell. And for rail, we include all electric technologies, which are light rail, heavy rail, and streetcar, and also diesel electric technologies, which are primarily commuter rail. So now let's take a look at the architecture of the calculator. The calculator has 4 modules, in total 10 components. It's a spreadsheet-based model, and at the very beginning, FTA was very specific about this model having no macros and should be able to operate on Excel 2007. So we built the model to that specification. Being a spreadsheet model, anybody can download it. Not anybody can use it. So let's go through and take a look at some of the inner workings of each module. And the first one, before I go into that, I wanted to explain how generally the workflow goes. So first of all, there is the scenario setting module that gives the context of the geographic location of the transit agency. It processes the meteorology and terrain for the location of the transit agency. And then these inputs feed into the energy consumption modules, which include the scale attractive power processor, the hybrid energy model, which deals particularly with hybrid technologies, and the rail duty cycle model, which deals with rail technologies. And then the energy consumption results go into the on-road emission rate modules, which include a MOVES matrix for bus technologies and rail emission rates. Then we also link the energy consumption to the GREET fuel cycle emission rates to obtain well to pump emissions. And there is also a cost effectiveness module that estimates the dollar per ton of CO2 reduction for different technologies. And then there is the summary output component. One of the most important components of the calculator is the scale attractive power processor. For those of you who are familiar with MOVES, you know that this is the approach that MOVES uses for heavy-duty vehicles. So we built our own spreadsheet functions based on the MOVES approach, but we also added additional flexibilities to deal with terrain, or so to speak, road grade and passenger loading. The spreadsheet calculations translate second-by-second speed time traces into operating mode bins. And we have 14 built-in representative duty cycles that users can choose from, or users can provide their own duty cycle of up to 3,000 seconds. And this is a very convenient feature because nowadays with modern-day technology, a transit agency can easily use a GPS logger and record their own duty cycle so that they can have their agency-specific duty cycle for analysis. This is the user interface as as it appears in the calculator. A user normally does not have to interface with this particular sheet, but I just wanted to show how the duty cycle is taken in this column, and then we calculate the different operating mode. So the duty cycle is taken in this column, and we calculate the different operating mode bins and summarizes up here. And these results feed into different other components of the calculator. So a little bit on the hybrid energy model. The hybrid energy model incorporates motive power distribution between the conventional engine and the electric motor, and we'll also consider the energy recovery through regenerative braking. And the goal here, even though we calculate the balance for each second of the duty cycle, the goal is not for this calculator to be a high fidelity simulation tool. Instead, we strive to achieve overall accuracy at the duty cycle level. So this is an example of how we process a route. This is the Orange County Transit Authority duty cycle. Here, as an input, we have the speed time trace, second-by-second speed. We model the second-by-second state of charge for the battery, the scale tractive power, and the split between the electric motor power and the engine power. The rail duty cycle model includes two models. The one separate model for the diesel electric transit trains and one separate model for all electric transit trains. And again, the rail model utilizes second-by-second trip data as well, and it considers a lot of different inputs specific for rail technologies, including track grade, wind resistance, and weather conditions. And this is a quick example of how we would process a speed time trace for a rail and translate it into a throttle profile, and then link the distribution to the rail emissions and get the fuel consumption and emissions. And then I wanted to introduce the MOVES matrix that's embedded in the calculator. And this is a very powerful component of the calculator. We ran MOVES 4,320 times for this particular version, and in our current work, which we're expanding the calculator, we're running MOVES a lot more times, tens of thousands of times. So MOVES is run in project mode with different combinations of fuel, temperature, and operating mode bins. So the vehicle activity, which is quantified in the STP processor, is now linked to the operating mode bin emission rates. And this is a screenshot of the matrix. This is just a corner of it, and so we basically look up the emission rates, and these numbers are the pollutant IDs as appear in MOVES. So we look up the emission rates by the source type, which is the type of vehicle, and by the operating mode bin, the model year we're examining, and the fuel. So I won't spend too much time on the details of the model. I wanted just to point out that we verified the modeling results in two published papers for bus and for rail, and our results fall within reasonable ranges according to prior research. So I wanted to go through some examples. First, let's look at the user interface this is the main input-output sheet for bus technologies. So the yellow cells are the cells that require user input. And all I wanted to point out is, despite all the technical components of the calculator that I just went through, there aren't that many user inputs that this calculator require. All we ask is the location, the city of the transit agency operations, the season that you would like to focus on, and how hot your summer is and how cold your winter is if you're looking at winter, and your inventory year, and your duty cycle, and the type of bus, whether it's the full-size transit buses or paratransit vans. And then the rest is, typical stuff for your route length, average passenger loading, and number of rounds per year. And down here, these are your fuels, the fuel options that you would like to choose for each propulsion technology. And I also wanted to show the cost effectiveness sheet. So in this sheet, we give the dollar per ton of CO2 reduction for each technology. So in this calculator, we have included some default cost profiles for diesel buses, CNG buses, hybrids, battery electric buses, and hydrogen fuel cell buses. And a user has the flexibility to go in and modify these cost profiles or build their own cost profiles. But we did a comprehensive literature review and put together these default cost profiles for ease of use. And this is one of the example applications we use the calculator for. The first one I wanted to show is a comparison of duty cycles. So what we're looking at here on this slide is two routes from two transit agencies in Atlanta. The blue route we're looking at is an urban transit bus route collected from MARTA, the Atlanta Transit Agency, and the green route is the express bus route collected from the Georgia Regional Transit Authority, GRTA. So these two routes have very different operating parameters, even though they're both in Atlanta. The blue route has an average speed of 15.8 miles per hour, and the green route has an average speed of 60 miles per hour because it's mostly on the freeway. And we also modified the express bus route because when you want to compare alternative technologies such as battery electric buses, they are not able to operate at a speed higher than 60 miles per hour normally. So just to give you a flavor of the duty cycle, this is the urban transit route duty cycle that has relatively low speed and a lot of stop and go. And this is the express bus route that has sustained high speed, not so much stop and go. The stop and go condition will appear when the bus reaches the end of the freeway and comes into town. And even then, the speed is relatively high. So in order for a fair comparison for the battery electric buses to operate, we arbitrarily stretched this duty cycle and capped it at 60 miles per hour so we could get reasonable comparisons. So this is the result from the calculator. It's published in a conference proceeding by ASTE. So what I wanted to point out here is the relative performance between the hybrid technologies and CNG, for example. For the urban bus cycle, you can see the advantage of hybrid technologies over CNG, but on the contrary, for the express bus cycle, CNG performs much better than the hybrid technologies. And this is an example to show that a transit agency's decision for fleet planning really depends on the type of operations they run. And the next example I wanted to show concerns geographic locations, and I chose San Francisco, California, Phoenix, Arizona, and Atlanta, Georgia as examples. So San Francisco, the three locations have different electricity generation mix, has very different terrain. San Francisco is very hilly. Phoenix is mostly flat. Atlanta is somewhat hilly, but not nearly as hilly as San Francisco. And the three cities have very different summer weather as well. San Francisco is mild. Phoenix has dry heat. Atlanta is very humid. So and the calculator can take all of these characteristics into account. So here what I'm showing is a sample run from the calculator using the New York City bus cycle. The New York City bus cycle is a very low speed transit duty cycle that is appropriate for use in your inner city congested conditions. So under this assumption, the graph shows the relative performance of the different technologies. So in general, across all three cities, the hybrids perform better than CNG because of the low speed, frequent stop and go conditions. And battery electric buses perform very well as just as hybrids. But here, what shows is for battery electric buses, you can see the difference across the three cities, mostly due to the electricity generation mix. So California's electricity is not very carbon intensive, but in Georgia we do have a lot of coal plants. So you can see the CO2 emissions from battery electric buses differ quite a bit across locations depending on the power generation mix. And this is another example where I compared the per passenger mile emissions at different times of day for buses, vans, heavy rail, and commuter rail. And this is an application where if a transit agency is planning a new route and is considering a broad range of alternatives, they can get some high level big picture idea of fuel cycle CO2 emissions from the calculator as well. Some of the other applications include policy evaluations, which is one of the projects we're doing right now under NCST is to evaluate eco-driving, the effectiveness of eco-driving and anti-idle programs for heavy-duty vehicles. And so for this one, we use the calculator. We have the before training and after training duty cycles, and therefore we can evaluate the emissions difference from the different policy programs. And also, because the calculator gives both well-to-pump and pump-to emissions, and the calculator also gives greenhouse gases and air pollutants, we can do a lot of analysis in terms of environmental justice. So a lot of times an agency's focus is not only to minimize fuel consumption and greenhouse gas emissions. We also care about on-road emissions and whether or not the inner city low-income populations are disproportionately affected by tailpipe emissions. And the calculator's output will be able to provide a picture on this regard. And again, like I showed before, the calculator will facilitate cost-effective analysis, and we can do multi-criteria evaluations considering all of these factors: the greenhouse gas emissions, air pollutants, and cost. So in summary, the calculator considers life cycle, mostly fuel cycle, so from well to wheel, if you will, the fuel and emissions for alternative fuel transit technologies. And the calculator results showcases that the impacts of alternative options really depend on the local operating characteristics. And we have some ongoing research. We're currently converting the spreadsheet model to an online platform because the spreadsheet is reaching its limit as far as operations. The model right now is 33 megabytes and has more than 40 tabs. So it does take some time to launch and run. So we're translating the spreadsheet into Python codes, and we'll take it to an online platform for faster operations. We're also expanding the modeling scope to heavy-duty trucks. And that concludes my presentation. Thank you very much. Now
All right.
Take questions.
Thank you very much, Dr. Xu. That was great. And just for everybody on the line, again, you're currently in mute mode. We will be soon taking questions. And if you have a question, you can actually ask it at any time using the chat function of the webinar software. That's on the lower left-hand corner of your screen. There should be a little box that you can type questions in. If you have questions on a particular slide, and again, you can download those slides from our website at policyinstitute.ucdavis.edu on the webinar tab. Please indicate the slide that your question is related to, or if you have a general question, just go ahead and ask that. But before we turn to questions, I want to introduce Tommy Edwards, who is, we're very happy to have participating in this webinar. Tommy is the Deputy Chief Performance Officer of the Sunline Transit Agency, and Sunline has really been a leading agency in terms of sustainable transit technologies and operations. They're located in Thousand Palms, California, and Tommy comes to us with more than 45 years of heavy-duty truck and bus fleet experience. He's an expert on the use of alternative fuels in heavy-duty transit buses, has experience with CNG, hethane, HCNG, hydrogen CNG, methanol, battery electric, hydrogen fuel cell powered vehicles. So a really excellent background and is going to provide us a perspective on his perspective on this tool and how it might be useful for transit applications. So Tommy, if you can hear me, and hopefully you're unmuted, go ahead and take it away.
Thank you, Anthony, and I'd like to thank Laura and the group for inviting us to participate today. One of the things that I know Anthony mentioned, the different types of fuel technologies that we've been involved in and that I've had the opportunity to work with. Over the last over 20 years here at Sunline, we've been 100% alternative fueled for all of our vehicles. And we've ran the gamut of trying different types of technologies and fuels. We serve the Southern California desert area, about 1,200 square miles of service. And we run the gamut of very hot temperatures, some our duty cycles are a little different. Some rural, some inner city. The thing that I'd really like to focus on with this presentation and the tool that I think it brings that we could have used many years ago. Now we have a tool. We didn't have that tool when we were trying to choose different technologies and fuels. And I really believe that by being able to model our particular duty cycles or other transit agencies would be able to do the same, and include several different types of vehicles or technologies for when considering different routes and types of service that we provide. We currently operate mostly CNG vehicles. We have for over 20 years, but we also have been looking at other technologies for the last 12 to 14 years, which includes some hydrogen fuel cell vehicles. We're currently operating 4 hydrogen fuel cell 40-foot buses in service here at Sunline, along with our CNG fleet. So for me, as a transit agency user of a tool like this, I really believe that bringing this forward is going to be very helpful. I get lots of phone calls all the time from other properties that are trying to make some decisions on what type of technology they might be looking at, and we're a firm believer here at Sunline that there's several great technologies out there, advanced technologies, and not any one is the silver bullet. And this model provides, from what I can see, the opportunity to utilize several technologies and using specific data from each property's duty cycles and the availability of fuels and the costs and so on and so forth, that would help immensely. So for me, one of my questions to the group, or to the presenter and the group, is to understand that weather plays a big role across the country, and for me here at Sunline, we operate our buses in up to 120 or even higher degree weather in the summertime, which increases the need for the air conditioning and other things. So I think I wanted to understand if that there's a way to differentiate the climates and weather conditions in this model.
Thank you, Tommy. And so, yeah, that's a great question, and also very coincident with one of the questions that came in from the listeners. So, Dr. Hsu, do you have a sense of sort of how weather factors into this and the extent to which it affects the results?
Absolutely. So we have in the calculator built in 12 different representative climate conditions. So 6 conditions for summer and 6 conditions for winter. And we do, let me pull up the slide and show you. So right here, I think one of the questions was how you factor in the severity index. So the way we consider the climate conditions, the weather conditions, is for summer you choose between 1 to 6 from very mild summers to very hot summers. And if you change the cell, so in the spreadsheet, this is a pull down menu, and if you change the value here, you'll see the description change right over here. There's a description, and it gives the temperature and humidity And if you would like to know a little more about how these things are categorized, there is a meteorology lookup sheet in one of the tabs. So you do have to scroll down and find the meteorology lookup sheet that has the 12 representative conditions listed. So we chose 12 cities across the country, 6 for summer, 6 for winter, to represent a range of different conditions.
Excellent, thank you. So a few other questions coming in here, and again, I welcome questions to either Dr. Hsu or Tommy Edwards at Sunline, and both of you guys should feel free to jump in if you have some thoughts on it. So you addressed this to some degree, Dr. Hsu, in your slide that showed a differentiation of results that varied across geographic region, and in particular the battery electric vehicle or battery electric bus showed a wide variation based on that. Is the life cycle associated with the fuel, so in that case it would be electricity generation, is it disaggregated at the state level? I guess it's a question. And then if you had further differences even within states, so for example, Sunline Transit's electricity is different than the Alameda County transit grid electricity. Is that in the model, or is that something that you might be able to easily change to reflect the local conditions?
Right now, within the calculator, it's down to state level. So the calculator itself, just by automatic calculations, cannot reflect anything finer than state differences. But it is possible for an advanced user to go to the eGrid tab. So there is an eGrid tab if you have the tool available. The eGrid tab has the electricity emission rates. So an advanced user could go in there and change the default values to whatever that's suitable for their own conditions.
And then I guess a similar question would be for other fuels that might be used. For example, hydrogen has a variety of different production pathways.
Yes, absolutely.
Okay, so that
for hydrogen in our calculator, we uses the default inputs from GREET. So it's assuming that hydrogen is from North American natural gas, and if a transit property has a different source of hydrogen, you can go into the GREET lookup sheet and change the default.
Great. So some other questions here, and again, if you have a question, please feel free to type it into the chat box, and we'll try to get to all of your questions in the remaining time that we have. So the next one is an interesting question. It's is there any way to use this model to compare, for example, transit travel with passenger travel? In terms of comparing, adding transit operations and perhaps displacing auto travel. Is that?
Yes, but it is seeing the future works. So coming back to this slide, we currently are working on adding the passenger cars to the spreadsheet model so that you can easily pop in the passenger travel into the same framework and have a overall comparison. But that's in the works. So like I said, we're expanding this model to all heavy-duty trucks, and in the process, we're updating the MOVES emission rates to MOVES 2014, because right now in the calculator it's MOVES 2010 emission rates. So we're updating all the emission rates to 2014 emission rates, and we're adding heavy-duty trucks and passenger cars.
So thanks for that. And actually, that relates to another question. And just to verify, so when you update to MOVES 2014, are you also going to be updating the transit bus emissions rates?
Yes. Yes.
Okay, great.
And in the process, we'll add school buses too.
Excellent. So you touched on this in one of your slides as it related to sort of the verification aspects of the tool. This question has to do with how, I'll read it here, how well do the fuel consumption module simulation results for diesel and the alternative fuel vehicles correspond to real-world test results? That's one question, and then I guess the other is, have you benchmarked this against other simulation software and what they say about those differences?
So in the current verifications we've done, it's mostly compared to prior research. So that includes a range of real-world testing and other simulation software. But we did not do our own testing, but we did compare ours to the literature. Great.
This is a question about, you'd mentioned that this was presented at ASCE, and I guess the question was there a paper that was associated with that, and then a comment, I could see wanting to share this with transit operators in our region for the purposes of fleet decisions and fleet purchases. So that's a question, and then actually I would invite Tommy to reflect on that latter part in terms of how this might be used to inform the fleet purchases. So first to you, Dr. Xu.
Yeah, that's wonderful. So I listed the references here on this slide. We have so this paper is published as a conference paper, and I believe you can find it if you just type in this reference and download it from the ASCE website. And similarly, this chart is actually from a paper as well, and I have included the reference here as well.
Great. And Tommy, do you have any thoughts on just sort of the nature of fleet purchases and the way in which this could be used for that?
I think primarily this opens the door to be able to do some modeling specifically for your property and your route structures that would help with planning of fleet purchases. So I believe the way I would see it being used more in the aspect of what technologies meets the criteria that the agency's long-range plan is going to be moving towards. So again, it would have been nice to have had a tool like this in the past. Now that we see there is a tool like this available, I think it's going to be very important that it gets out to the properties and how they may be able to use this when they're planning their technologies that they are looking at using in their bus and fleet purchases. So I see it as a great tool moving in that direction.
Excellent. Thanks. So a couple questions relating to sort of the economics component of this. So you most of your presentation focused on kind of the emissions performance, but you also included the economics. Is the costs that are reflected in the model also include sort of the vehicle depreciation or amortization costs, or is that just fuel costs? So that's one question. And then the second one is, a lot of these technologies are relatively new, or some of them I should say, and there is expectation for future cost reductions. Is your cost information in here sort of near-term costs, mid-term costs, long-term costs? And again, I guess the question would be if that's something that's editable by the user.
Yes, absolutely. So the cost profiles, first question, the cost profiles include the purchase price, facility construction if you have to add new facilities because of the technology, and the operating and maintenance costs, including your labor, your fuel, and the end of life, so salvage, and amortization included in that whole life cycle. So the cost profile that we have built into the calculator includes the whole life cycle cost. And this spreadsheet is completely open source, and anybody can download and edit any portion of it. The cost profiles we have included are near-term costs. So we search the literature for published results of existing costs, mostly from FTA reports and some of the Energy Information Administration's published results. So that is near-term results. But if a user would like to project into the future and have reasonable projections, and you can always build your own cost profiles in that cost profile sheet.
So just to maybe follow on then, is the sort of the default values, are those based on near-term costs, expected long-term costs, something in between?
The built-in costs are near-term costs.
That's the defaults. Okay, gotcha. Okay, a question from our other panelist here. Tommy, you want to ask it? I'll go ahead.
Yeah, I can ask it. Ann, in your model where you for hydrogen, you mentioned that you used the North American natural gas as the feedstock for producing the hydrogen. Can the model adapt to, say, using bio landfill gas for the feedstock? Here at Sunline, we've just recently moved to biogas purchase for all of our fuel.
Yes, absolutely. So it would require a little bit advanced knowledge of the model to find the upstream emission rates. But there is, towards the end of the tabs, there is a tab called Upstream Emission Factors, and in there it has the hydrogen emission factors pulled from GREET. And so a user could change that, and I really appreciate your comment, Tommy, and I think in the next version I'll just include more pathways for hydrogen to have them as built-in functions within the calculator so that the user doesn't have to manually change them.
Okay, that's excellent. That seems very useful to be able to move between those different. You've put the model together so that it's adaptable, and I think that's very important.
Yeah, no, I agree, and I think one of the great things about a lot of these different tools and generally models that are worked on through the National Center, and we're expected to cover some more of those in later webinars, is that really becomes sort of a platform for understanding the implications of different choices to support decision making, and also to appreciate and understand sort of the sensitivity to different parameters, and certainly the production pathway cycle for different fuels is a major factor in especially the emissions performance. I have a very specific question here relating to the model, and I'll just read it. Dr. Xu, you may be able to provide some perspective. It says the op mode summary sheet seems to have constants for energy consumption rate. The question is, are these based on actual recorded cycles, and can those values be used for different or another drive cycle?
I am actually not quite sure about which constant Ram is talking about, but if he's talking about the energy consumption rate for a specific operating mode bin, as summarized in the op mode summary sheet, those operating those fuel consumption rates are based on moves. So whatever moves has as the fuel rate for a specific bin, that's what we have.
Excellent, thanks. Actually, maybe if you, this is sort of a general question, Dr. Hsu, which is with respect to as you've run the model, and you could answer this either in relation to the emissions performance results or the economic results. Can you maybe provide a couple of insights that you've picked up on what is the model most sensitive to in terms of those results, and kind of what have you learned from running it for different types of conditions, different locations, different fuel pathways?
I would say duty cycle and the location. And in terms of location, I think the power generation mix is the most significant for battery electric buses. But definitely duty cycle. And sometimes it's really hard to say, like as I pointed out here on this slide, that between San Francisco, Phoenix, and Atlanta, there are many things that are different across the three cities. And here I actually compared them by the same duty cycle. Well, in fact, the three cities will probably have each of their own duty cycles. So when it comes back to the idea that you really ought to evaluate your options within your own context, because a lot of these characteristics, the effects are not additive, if that makes sense. So, for example, if a hotter climate gives you more, requires higher fuel consumption, yet a flatter terrain requires less, the relationship is not linear. So you can't just say, okay, well, a hotter climate plays a more important role. It depends really how hot it is and how rough the terrain is.
Yeah, no, those are great points. And actually, I was going to ask you to define duty cycle, but I think you sort of did there, which is that it's reflective of the operational characteristics of the vehicle, which includes speed, acceleration, distance, and terrain, and of course climate as well. So that's great.
Yeah, I guess. Yeah, sorry I didn't clarify it earlier. A duty cycle really is just a fancy term for a speed time trace. So in our context, when we ask for a duty cycle input from a user, we really only are asking for the second-by-second speed. From there, we calculate the acceleration and the engine load.
Excellent. Great. So I think that's actually we've sort of come to the end of our questions, and we're also at the end of our webinar time here. So I just want to sort of close and thank our presenter as well as our discussant, so Dr. Hsu and Tommy Edwards from Sunline Transit. This, I think, has been quite informative. If folks have further questions for Dr. Hsu, we can provide the contact information. Also, there were some questions about some of the references, and we'll work with Dr. Hsu. For those that are publicly available, we can cross-link those to our webinar page, so that'll be updated. For those of you who've dialed in, I want to thank you both for participating and for your good questions. Also, you will be receiving a survey subsequent to this webinar, and we really encourage you to fill that out, provide us feedback both on how you thought this one went, as well as any thoughts you might have for future webinars. We're always looking for opportunities. We definitely will be having more webinars in partnership with the National Center for Sustainable Transportation, so please keep an eye out in your email inbox for the invitation to those. And again, this was recorded, so the webinar will be posted on our website. If you have colleagues that you think might be interested, please feel free to direct them to that. That'll also be on the webinar page. So thank you, everyone, and have a good rest of your day, and hopefully we'll hear from you again. Thanks a lot, Tommy. Thanks a lot, Dr. Hsu.
Thank you, Tommy.
All right. See ya.